The linear transformation y is equal to ax transforms a column vector x into another column vector y by means of a square matrix A, where A is written as A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN, and where x is x1, x2, like this xn, and y is y1, y2, yn. If a vector x is transformed into a scalar multiple of the same vector, that is, x is transformed into lambda times of x, that is lambda is a scalar and x is transformed into scalar multiple of the same vector, that is x, then we can write y is equal to ax, that is equal to lambda times x. From this we can write ax is equal to lambda x, or a minus lambda I x is equal to 0, where I is the unit vector of order n. Now this we can write as a11 minus lambda x1 plus a12 x2, like this, a1n xn equal to 0. a21 x1 plus a22 minus lambda x2, like this, a2n xn equal to 0. That means we are just subtracting the scalar lambda from the diagonal elements. The last equation is 1n1 x1 plus 1n2 x2 plus ann minus lambda xn equal to 0. Now this system of equations will have a non-trivial solution. We'll have a non-trivial solution when determinant of a minus lambda I is equal to 0. That means a11 lambda, a12, a1n, a21, a22 minus lambda, a2n, like this, an1, an2, ann minus lambda is equal to 0. Represent this equation as 1. Now this equation 1 has a name. It is called the equation of transformation, or it is called characteristic equation of matrix A. Now we can see that a minus lambda times I, this is nothing but a polynomial of degree n in what? In lambda. It's a polynomial in lambda of degree n. And this polynomial is called polynomial of the transformation, or called the characteristic polynomial of matrix A. If we solve this equation, what we get? We get n roots. As it is a polynomial of degree n, we get n roots for what? For lambda. And these roots are called, that is, we are getting n roots of lambda. Say these roots be lambda 1, lambda 2, and lambda n. These roots of this characteristic equation has a special name called the characteristic roots or called eigenvalues of A. Now, what is eigenvectors? Here comes the eigenvalues. Now, what is eigenvectors? Corresponding to each value of lambda, that is, say lambda 1 or lambda 2, like this lambda n, corresponding to each of these values of lambda, the equation Ax is equal to lambda x has a non-zero solution vector. Solution vector. Say, let for lambda is equal to lambda r, the non-zero vector be x is equal to xr, which satisfy the given equation, that is A xr is equal to lambda r xr. Then this xr is called the eigenvector of matrix A corresponding to the eigenvalue lambda r. So when this equation is satisfied for a particular value of lambda by a non-zero scalar vector xr, then that xr is called the eigenvector of matrix A corresponding to eigenvalue lambda r. One thing that is very important is that eigenvalues and eigenvectors are defined only for square matrices. Now we will consider a given matrix and we will find out the corresponding eigenvalues and eigenvectors of the matrix. Take example 1. Let A be a 2 cross 2 matrix. A must be a square matrix. Minus 1, 2. Now, what is the procedure of getting the eigenvalues and eigenvectors of the matrix A? First, determine its characteristic equation. That is, A minus lambda I is equal to 0, where I is a 2 cross 2 identity matrix. Now, this implies this we can write as 7 minus lambda 6 minus 1, 2 minus lambda, that is equal to 0. Solving this equation, so now we expand the determinant as 7 minus lambda into 2 minus lambda plus 6 is equal to 0. Simplifying this, we get lambda minus 5 into lambda minus 4 is equal to 0. Hence lambda is equal to 4 and 5. Since it is a 2 cross 2 matrix, we get 2 roots for lambda. Similarly, for 3 cross 3 matrix, we will get 3 roots for lambda, 3 values for lambda. Now, these denotes the eigenvalues of matrix A. Now, how to deduce the eigenvectors corresponding these eigenvalues of the eigenvectors are given by the equation Ax is equal to lambda x, which we can write as A lambda I x equal to 0. Hence, in this case, we can write the eigenvectors are given by the equation 7 minus lambda. Let me write it in elaborate form. A is here 7 minus lambda 6, that is minus 1, 2 minus lambda. Ax is say x1, x2 and 0. From this we can write 7 minus lambda x1 minus x2 equal to 0, 6x1 plus 2 minus lambda x2 equal to 0. This equation gives eigenvectors for the lambda is equal to 4 and for lambda is equal to 5. Now say lambda is equal to 4. Hence the equation becomes, putting lambda is equal to 4, 3x1 minus x2 equal to 0 and 6x1 minus 2x2 equal to 0. From this we can write x2 equal to 3x1. Hence, any eigenvector corresponding to lambda equal to 4 can be written as v1, that is vector 1, 3. Similarly, when lambda is equal to 5, the equation becomes 2x1 minus x2 equal to 0 and 6x1 minus 3x2 equal to 0. From this we can write 2x1 is equal to x2. Hence, corresponding to the eigenvalue of lambda is equal to 5, the corresponding eigenvector v2 can be written as 1, 2. This is x1 and this is x2. Now we are getting this eigenvector corresponding to lambda is equal to 4 and this eigenvector corresponding to lambda is equal to 5. Now from the above example, note that vector v1 is not only the one eigenvector associated with matrix A. Any non-zero scalar multiple of vector v1 is also an eigenvector of A associated with the eigenvalue lambda is equal to 4. That is, we can also take v1 as 2 times some scalar multiple of v1, that is equal to 2, 1, 2, which is equal to 2, 6. Now this is also denote an eigenvector corresponding to the eigenvalue lambda is equal to 4. And this similar statement also hold for eigenvector v2. Hence what we can conclude eigenvectors corresponding to eigenvalue is not unique. Eigenvector corresponding to a particular eigenvalue is not unique. That is, some scalar multiple of that particular eigenvector, but the scalar is non-zero, also denote the eigenvector of the matrix corresponding to the same particular eigenvalue. Consider another example. Now take matrix A as a 3 cross 3 matrix. 0, minus 2, minus 1, 5, 7, 1 and 7, 7, 4, and find the eigenvalue and eigenvectors. First, write the characteristic equation, that is A minus lambda I is equal to 0, where lambda is here a 3 cross 3 identity matrix, which can be written as minus lambda minus 2 minus 1, 5, 7 minus lambda 1, 7, 7, 4 minus lambda is equal to 0. Expanding the determinant and after simplifying, finally we will get lambda minus 2, lambda minus 4, lambda minus 5 is equal to 0. Hence eigenvalues are 2, 4 and 5. These denote the eigenvalues of the matrix A. Now eigenvector, we will evaluate the eigenvector corresponding to lambda is equal to say 5. Say lambda is equal to 5. What is the corresponding eigenvector? Now the corresponding eigenvector must satisfy the equations, that is the set of equations here will be minus lambda x1 plus 5x2 plus 7x3 equal to 0, minus 2x1 plus 7 minus lambda x2 plus 7x3 equal to 0. The last one is minus x1 plus x2 plus 4 minus lambda x3 equal to 0. So when the eigenvector must satisfy this equation. So when lambda is equal to 5, the equation becomes, putting lambda is equal to 5, we get minus 5x1 plus 5x2 plus 7x3 equal to 0, minus 2x1 plus 2x2 plus 7x3 equal to 0, and finally minus x1 plus x2 minus x3 equal to 0. Just write it 1, 2 and 3. From 1 and 3 we can write minus 5x1 plus 5x2 plus 7x3 equal to 0. You can solve this system of equations by any method you are comfortable in. And we are multiplying 5 times 3 minus 5x1 plus 5x2 minus 5x3 equal to 0. Solving this we get x3 equal to 0. Now we put x3 is equal to 0 in equation 3 and we get x1 minus x2 is equal to 0. From this we can write x1 is equal to x2. Now let x1 is equal to s, where s is any arbitrary non-zero constant. Remember, it must be non-zero. Hence the solution is the corresponding vector, that is the elements are x1, x2, x3. We can write it as x1 is equal to s, x1 is equal to x2, hence x2 is equal to s, and x3 is equal to 0, this. Taking s common, we can write 1, 1, 0. Hence 1, 1, 0 is an eigenvector of the system associated with the eigenvalue lambda is equal to 5. This is a particular eigenvector. This is one. There may be many eigenvectors depending on the value of s. Here we are taking s is equal to 1 and we are getting one particular eigenvector corresponding to lambda is equal to 5. Usually, one thing I will mention here, usually the eigenvectors are normalized and the resulting vector represent the normalized eigenvector of the defined system. Then how to normalize an eigenvector? To normalize a eigenvector, just determine its magnitude by taking square roots of the square of its components and divide each element by the magnitude. In the above case, in the previous example, the normalized vector of matrix A is written as 1 divided by magnitude 1, 1, 0. Say it would be n1, where magnitude is the square root of square elements of the components, that is 1 square plus 1 square. Magnitude is square root of 1 square plus 1 square plus 0, that is equal to root 2. And finally we can write n1 as equal to 1 by root 2, 1 by root 2, 0. This is the normalized representation of eigenvector. Also note that any non-zero scalar multiple of this normalized eigenvector is also an eigenvector of the system. Next, consider example 3. Obtain eigenvalues and eigenvectors of matrix A, where A is equal to 5, 8, 16, 4, 1, 8, minus 4, minus 4, minus 11. First step is write the characteristic equation, that is 5 minus lambda, 4 minus 4, 8, 1 minus lambda minus 4, 16, 8 minus 11 minus lambda, that is equal to 0. After expanding the determinant and simplifying, we will get lambda plus 3 whole square to lambda minus 1 is equal to 0, from which we can write lambda is equal to 1, minus 3 and minus 3. These are the eigenvalues of the matrix, where one eigenvalue is 1 of a multiplicity 1 and another eigenvalue is minus 3 of multiplicity 2. Now what is the eigenvector corresponding to lambda equal to 1? The eigenvector corresponding to lambda is equal to 1 satisfies the equation 4x1 plus 8x2 plus 16x3 equal to 0, 4x1 plus 8x3 equal to 0. The last one is 4x1 minus 4x2 minus 12x3 equal to 0, which on simplifying we can write x1 plus 2x2 plus 4x3 equal to 0, x1 plus 2x3 equal to 0 and x1 plus x2 plus 3x3 equal to 0. Now from this we can write x1 is equal to minus 2 times x3. Now let if x3 is equal to let s be any arbitrary non-zero constant, non-zero real number, then x1 is equal to becomes minus 2s, and from this we get x2 as minus x1 minus 3x3, that is equal to 2s minus 3s, that is equal to minus s. Hence we can write the eigenvector x1, x2, x3 as equal to s times x1 is minus 2, x2 is minus 1 and x3 is 1. Hence 2 minus, for s is equal to 1, 2 minus 2 minus 1 and 1 denotes a particular eigenvector of the matrix A corresponding to eigenvalue lambda is equal to 1. Now what is the eigenvector? What is eigenvector corresponding to eigenvalue lambda equal to minus 3? Here minus 3 is a double root of the characteristic equation. It is of multiplicity 2 because it is repeated 2 times. Then the eigenvector corresponding to lambda is equal to minus 3 must satisfy these equations. 8x1 plus 8x2 plus 16x3 equal to 0, 4x1 plus 4x2 plus 8x3 equal to 0, minus 4x1 minus 4x2 minus 8x3 equal to 0. Here we see that all these equations are equivalent to a single equation, that is x1 plus x2 plus 2x3 equal to 0. Hence independent eigenvectors can be obtained by giving arbitrary values to any two of the quantities x1, x2 and x3. Here say we apply arbitrary values to x3 and x2. We apply x3 is equal to t and x2 is equal to s, any two values, where s and t are what? Any arbitrary non-zero real number constant. Hence x1 is written as minus s minus 2t. Then the eigenvector corresponding to lambda is equal to minus 3 have the form minus 1 1 0 multiplied by s plus minus 2 0 1 multiplied by t, where s and t are any arbitrary non-zero constant. Hence, these are the method of evaluating the eigenvalue and eigenvectors of a given square matrix. Now, another example we can consider here, say 4. Find the problem is that find the sum and product of the eigenvalues. That is, we have to find out the sum and product of eigenvalues of the matrix A, where A is equal to minus 1 1 1 1 minus 1 1 and 1 1 minus 1, without determining the roots. Here we have to find out the sum and product of the eigenvalues without determining the roots of the characteristic equation. How we can do it? Here one thing you have to remember, that sum of eigenvalues is equal to the, that is eigenvalues, how many eigenvalues will be there? 3, lambda 1, lambda 2 and lambda 3. This is equal to the trace of A, trace of matrix A. What is trace of matrix A? That is equal to the sum of the diagonal elements. Hence minus 1 plus minus 1 plus minus 1, which is equal to minus 3. This is the sum of eigenvalues. Similarly, another thing is that product of eigenvalues, that is lambda 1 into lambda 2 into lambda 3, is nothing but the determinant of the matrix. Here determinant of this matrix is 4. You can cross check it, that by following the traditional method, if you find out the eigenvalues of A, you will get these as minus 2 and 1. Here check that sum is minus 3 and product is 4. Next comes properties of eigenvalues and eigenvectors. First is that a matrix A and its transpose have same eigenvalues. If lambda denotes the eigenvalues of A, then transpose of the matrix have identical eigenvalues. Property 2 is that the product of the eigenvalues of the square matrix A is determinant of A, that we have seen before. Note that if A is non-singular, suppose A is non-singular, then we can write determinant of A is equal to 0. Then we can conclude that at least one of the eigenvalue is 0, and also vice versa. 3 is that, say A is a square matrix n cross n of order n. So its eigenvalues be lambda 1, lambda 2, like this lambda n. Then first thing is that k times of lambda 1, that is k times of each eigenvalue, that is k lambda 1, k lambda 2, like this k lambda n, are eigenvalues of k times of A, where k is any non-zero scalar. Second thing is that if suppose here is lambda 1, lambda 2 and lambda n are eigenvalues of A, then we can say that 1 minus lambda 1, 1 minus lambda 2, that is inverse of the eigenvalues, lambda n are eigenvalues of what? Eigenvalues of A inverse, provided lambda r is not equal to 0 for r is equal to 1 to n. Third is that lambda 1 to the power p, lambda 2 to the power p, like this, lambda n to the power p are eigenvalues of a to the power p, where p is any positive integer. Another property is that a matrix is invertible if and only if none of its eigenvalues is equal to 0. That means a matrix is invertible, that means the matrix is the inverse if every eigenvalue of it is non-zero. And inversely and conversely, if each eigenvalue of a matrix is non-zero, then the matrix is invertible. And fifth property is that the eigenvalues of a triangular matrix, whether it is upper triangular or lower triangular, then the eigenvalues you can calculate not by the traditional method, just the diagonal elements are the eigenvalues of the triangular matrix. This is one triangular matrix. Then what is the eigenvalues of this matrix? Just A11, A22 and A33. Next I will discuss some theorems. One is that the eigenvalues of an orthogonal matrix, that is if A is an orthogonal matrix, then its eigenvalues lambda are plus 1 or minus 1. Theorem 2 is that the eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix are orthogonal. That is, the eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix are orthogonal. And theorem 3 is that the eigenvectors corresponding to distinct eigenvalues of a matrix are linearly independent. That is, the eigenvectors corresponding to distinct eigenvalues of a matrix are linearly independent. And in later I will discuss what is linear independence and what is the condition that a set of vectors is linearly dependent or independent. Now next theorem is that the eigenvalues of a real symmetric matrix are all real. We can verify this theorem. Say A be a real symmetric matrix. 0, 1, 1, 1, 0, 1 and 1, 1, 0. The statement of the theorem is that the eigenvalues of a real symmetric matrix are all real. This is the statement of the theorem. Now to find out the eigenvalues of this real symmetric matrix, we write down the characteristic equation, that is equal to minus lambda 1 1, 1 minus lambda 1 and 1 1 minus lambda, which is equal to 0. After simplifying this equation, we get lambda plus 1 and lambda minus 2 is equal to 0. Here it will be lambda plus 1 whole square into lambda minus 2 is equal to 0, from which we get lambda is equal to minus 1 and 2. See, all these eigenvalues are real. Next, I will state what is Cayley-Hamilton theorem. According to the Cayley-Hamilton theorem, every square matrix satisfies its own characteristic equation. What is its statement? Every square matrix satisfies its own characteristic equation. That is, if A is an n cross n matrix and the characteristic polynomial of AB C0 x to the power n plus C1 x to the power n minus 1 and Cn, then by Cayley-Hamilton theorem we can write C0 a to the power n plus C1 a to the power n minus 1 like the Cnin is equal to 0. We can write this. One important conclusion to be drawn from this theorem is the fact that a matrix taken to a certain power can always be expressed in terms of sums of lower powers of that matrix. And Cayley-Hamilton theorem particularly gives a computational procedure for obtaining inverse of a matrix when A is non-singular, that is, the matrix is invertible. From Cayley-Hamilton theorem, we can compute its inverse. Say for example, let A be 2, 1, 1, 1. It's a 2 cross 2 matrix. Characteristic equation we can write it as 2 minus lambda 1, 1, 1 minus lambda is equal to 0. After simplifying, we can write lambda square minus 3 lambda plus 1 is equal to 0. Now, by Cayley-Hamilton theorem, we insert matrix A in place of eigenvariable lambda. So, replacing lambda by the matrix A, we write A square minus 3A plus 1 is equal to 0. This we can write. Next, which we can write also A minus 3I2 plus I2 equal to 0 or minus A minus 3I2 is equal to I2. Now clearly here we are getting A inverse is equal to minus A minus 3I2 and we calculate it as 2111 minus 3003, which we get as 1 minus 1 minus 1 2. This is A inverse. Now I will discuss some gate problems. Problem 1 is obtain the eigenvalues of the matrix, the given matrix. Solution is, clearly we can see that A is an upper triangular matrix, right? Hence eigenvalues are the diagonal elements. So we don't have to calculate it here. That eigenvalues are 1, 2, minus 2 and minus 1. Consider problem 2. The eigenvectors of the matrix, the given matrix, where alpha is not equal to 0 are what? Write down the characteristic equation. From which we get lambda cube equal to 0. Hence eigenvalue of the matrix is 0 of multiplicity 3 because 0 is repeated 3 times. Let x1, x2, x3 be eigenvector corresponding to lambda eigenvalue lambda is equal to 0. Then the equation becomes alpha x3 equal to 0, from which we can write x3 is equal to 0. Hence x1 and x1 we can write it as any arbitrary real constant and x3 must be 0. That is, the eigenvector is of the form CD0, where C and D are any arbitrary non-zero constant. That is, we can take C and x1 and x2 anything, but x3 must be 0. In the options given, see, in case of A, this is x3, which is alpha, that is not equal to 0. Hence, A is not the option. In case of B, x3 is equal to 0. Immaterial, what is x1 and x2, but x3 is equal to 0. So, B is the answer. In case of C, x3 is not equal to 0. So, C is not the answer. And in case of D, x3 is also 0. So, also D is the answer. So, here answer is 2. B and D. Now consider this problem. A is a given matrix. We have to calculate a to the power 4. Here we will apply Cayley-Hamilton theorem. First I will write down the characteristic equation, that is 1 minus lambda 0 0 0 0 minus 1 minus lambda 0 0 0 0 I minus lambda 0 1 minus 1 I minus lambda, that is equal to 0. After simplifying the determinant, we will get the equation. After simplifying the equation, we will get 1 plus lambda 1 minus lambda I plus lambda, and I minus lambda is equal to 0, from which we can write 1 minus lambda square I square minus lambda square equal to 0, or 1 minus lambda square minus 1 minus lambda square is equal to 0, or lambda to the power 4 minus 1 is equal to 0. Now applying Cayley-Hamilton theorem, we replace lambda by the matrix A and we get a to the power 4 is equal to 1. So our answer is 1. Next problem is a very simple problem. Just evaluate the eigenvalues of A. Just write down the characteristic equation. And simplify the equation, we get just expand the determinant and equate to 0. We get this, from which we can calculate lambda is equal to 0, 0 and 3. So our answer will be C. This is another similar problem. Which of the following is an eigenvector of the given matrix this? Similarly, proceed as usual. Determine the characteristic equation, that is 5 minus lambda 0, 0, 0, 0, 5 minus lambda 0, 0, 0, 0, 2 minus lambda 3, 0, 0, 1, 1 minus lambda equal to 0. Now expand this as 5 minus lambda into 5 minus lambda within bracket this equal to 0. From this we can write 5 minus lambda whole square lambda square minus 3 lambda minus 1 equal to 0. Here we can see that one eigenvalue is lambda is equal to 5. Now what is the eigenvector corresponding to this eigenvalue? Now eigenvector corresponding to lambda is equal to 5 must satisfy the equation. Putting lambda is equal to 5, we get minus 3x2 from this plus x3 equal to 0, and from this we get 3x2 minus 4x3 equal to 0. Now we have to solve this equation. Let x2 is equal to t. T is an arbitrary non-zero constant. Then x3 we can write it as Not in this way. Coefficient matrix. Consider the coefficient matrix of this homogeneous system, that is minus 3, 3, 1, minus 4. The determinant of this coefficient matrix is not equal to 0. Hence, by Cramer's rule, the system of equation this has a unique solution, that is the 0 solution. And we get x2 is equal to 0 and x3 is equal to 0. Hence, eigenvector will be x1 and x4 is any non-zero arbitrary constant, and x2 and x3 must be equal to 0. So in this option, in this case x2, x3 not equal to 0. In this case this is also not equal to 0. But in case of C, x2 and x3 both are equal to 0. Hence our answer is C. Problem 6 is eigenvalues of the matrix S, which is a 2 cross 2 matrix, are 5 and 1. Then what are the eigenvalues of the matrix A square? Here we don't have to calculate it. It trivially follows from the property of eigenvalues of a matrix. If eigenvalues of a matrix S are 5 and 1, then eigenvalues of matrix A square is nothing but 5 square and 1 square. That is, our answer is A. Problem 7 is A is a given A is any 2 cross 2 matrix, and the eigenvalues and the corresponding eigenvectors of the matrix are given as lambda 1 is equal to 8, and the eigenvector corresponding to lambda 1 is v1. Another eigenvalue of the matrix A is 4, and its corresponding eigenvector is v2. Then what is the matrix? Let the matrix A, B, C, D are its elements. Then Ax is equal to lambda x. This is the equation. First we put lambda is equal to lambda 1, that is equal to 8, and we get A, B, C, D. The vector is 1, 1 when lambda 1 is equal to 8, and lambda x is this. And putting lambda is equal to lambda 2, that is equal to 4, we get from this equation A, B, C, D 1 minus 1 is equal to 4 times 1 minus 1. From this we get A plus B equal to 8 and C plus D equal to 8. From this we get A minus B equal to 4 and C minus D equal to minus 4. Solving these 4 equations, we get A as equal to 6, B is 2, C is 2 and D is 6. Hence our answer is A. A is the given matrix. Next thing I will discuss linear dependence and independence of vectors. Consider a set of vectors as now this set of vectors is linearly dependent. If there exist scalars C1, C2 like this Cn, not all 0, such that C1, this vector, this equation, equal to 0. But if the only solution of this is C1 is equal to 0, C2 is equal to 0, that is all the scalars are 0, then we will say that the given set of vectors is linearly independent. These are the definition of linear dependence and independence of a set of vectors. In case of linear dependency, all CIs, all the scalars are not zero. But if all the scalars are zero, then the set of vectors is linearly independent. Consider some examples. Example 1 is, determine whether the following vectors are linearly dependent or independent. The vectors given as this. One is 0, 1, 4. Second is 1, 0, minus 3. And third one is 2, 3, 8. We have to determine whether these vectors are linearly independent or dependent. For this, how we will proceed? We need to solve this. Where C1, C2, C3 are scalars. This we can write it as putting the values of vectors. Which is nothing but this set of equations, C2 plus 2C3 equal to 0, C1 plus 3C3 equal to 0, and 4C1 minus 3C2 plus 8C3 equal to 0. Now consider the determinant of Aij, that is 0, 0, 2, 1, 0, 3 and 4 minus 3, 8. If you expand the determinant, you will see that this is not equal to 0. Hence we can apply Cramer's rule, and by Cramer's rule there exists unique solution of this system of homogeneous equations, and the unique solution is nothing but the zero solution. Hence we get C1 is equal to 0, C2 is equal to 0 and C3 is equal to 0. Hence from definition of linear independence, it follows that the given vectors are linearly independent. Next example is, examine if the set of vectors 2, 1, 1, 1, 2, 2 and 1, 1, 1 is linearly independent or dependent. Here similarly we will find three scalars C1, C2, C3, and we will get this as C2 times next vector and C3 times the third vector, from which we get a set of equations, that is 2C1 plus C2 plus C3 equal to 0 plus C1 plus 2C2 plus C3 equal to 0, C1 plus 2C2 plus C3 equal to 0. Now from these two equations we get C1 minus C2 equal to 0, which we can write C1 is equal to C2. Now let C1 is equal to K and C2 is then also equal to K. Now from this equation we get K plus 2K plus C3 is equal to 0, from which we write C3 is equal to minus 3K. Hence if we put K is equal to 1, we get C1 is equal to 1, C2 equal to 1 and C3 is equal to minus 3. From this, by definition of linear dependence of vectors, it follows that the given vectors are linearly, since these scalars are not all zero, the set of vectors are linearly dependent. Now, what is linearly independent eigenvectors? Linearly independent eigenvectors. The eigenvectors corresponding to a particular eigenvalue contain one or more arbitrary scalars. The number of arbitrary scalars is the number of linearly independent eigenvectors associated with that eigenvalue. That is, the number of arbitrary scalars is the number of number of linearly independent eigenvalues associated with a particular eigenvalue. Now consider an example. In previous section we have discussed example 3, in which case we considered the matrix 5 4 minus 4, 8 1 4 and 16 8 11. In that case we got the eigenvalue lambda is equal to 1 of multiplicity 1, that is it is repeated once, and we got lambda is equal to minus 3 of multiplicity 2, that is minus 3 is repeated twice. Now we have also seen that the eigenvectors with lambda is equal to minus 3 were found to be like this: minus 1 1 0 s plus minus 2 0 1 t, where s and t are non-zero arbitrary constant. Now there are two linearly independent eigenvectors associated with lambda is equal to 3, one for each arbitrary scalar s and t. So there are two linearly independent eigenvectors that is associated with lambda is equal to minus 3. Now we have also seen that for the eigenvector associated with lambda is equal to 1 is k minus 2 minus 1 1, where k is another arbitrary scalar. Since there is only one arbitrary constant here, that is k, there is only one linearly independent eigenvector associated with lambda is equal to 1. Combining the linearly independent eigenvectors corresponding to two eigenvalues lambda is equal to minus 3 and lambda is equal to 1, we get minus 1 1 0, minus 2 0 1 and minus 2 minus 1 1 as the maximal set of linearly independent eigenvectors of the matrix. So this is the maximal set of linearly independent eigenvectors for the given matrix, out of which 2 is related to lambda is equal to minus 3 and 1 is related to lambda is equal to 1. Consider this problem. What is the number of linearly independent eigenvectors of the given matrix 2 0 1 2? First, write down the characteristic equation. That is, first we have to find out the eigenvalues of the given matrix. That is 2 minus lambda 0 1, 2 minus lambda equal to 0. Solving this we get 2 minus lambda square is equal to 0. That is lambda is equal to 2 comma 2. That is eigenvalue is 2 of multiplicity 2. Now eigenvector corresponding to lambda is equal to 2 must satisfy the equation 2 minus lambda x1 plus x2 equal to 0 and 2 minus lambda x2 equal to 0. Putting lambda is equal to 2 we get x2 equal to 0. Hence eigenvector corresponding to lambda is equal to 2 is c times 1 0, where c is any non-zero arbitrary scalar. Since there exists only one arbitrary scalar, our answer is definitely B. That is, there exists one linearly independent eigenvector of the given matrix, this.